All right. Thanks a lot for the
Yeah,
really
please.
kind introduction.
Thank you.
Let me know if there are any issues with the audio or slides at any moment, and I'll go ahead and fix that. But for now, I'll go ahead and get started. I'm really excited to be here. Thanks a lot for the invitation to come give this talk. Excited to talk about something that's a little bit different from a lot of the things that we've seen so far in this conference. And that's going to be fluidic control and energy harvesting for wearable robots. And so I'm going to get into the technical aspects of the work in a moment. I usually like to start with this brief introduction slide. And a lot of this has already been said during the great introduction, but I have a few photos of the lab members here at the top, the brief bio sketch on the bottom left. And then I focused on some of our research areas here in the center. And broadly in the PyLab, what we're looking at is the intersection of energy, materials, and fluids. So it sounds like a very broad area of research, and it is. We have a lot of interesting projects in interfacial phenomena and heat transfer and thermodynamics. But today I'm going to focus on some of our work that's related more to the area of soft robotics and materials. And so there's been a big push recently, as a lot of you know, from hard traditional robots to their soft counterparts. And that could include things from actuation to sensing and even control and power systems. This makes a lot of sense for the audience here as people that are really interested in wearable devices. And this hasn't just been our group that's looking at this area. There have been other perspectives and manuscripts and even some predictions of the future performance of these soft devices that are very optimistic, I'd say. And quite recently, we actually had a review paper come out from our group where we analyzed almost 5,000 papers about soft robots and soft devices and tried to take a data-driven approach to look at the state of the art in this field, as well as look at the future directions that seem really promising. And in doing this, one of the things that we identified was that fluidic control seems to be quite underdeveloped in terms of this transition to soft componentry. And I highlight that in one of the figures from the review here, where we found that for soft robots or devices that did have a control component, the vast majority of these controllers were rigid materials and not soft devices. And so this seems to be a limitation for soft robots and devices. We also see that the majority of these control systems, if we look at this diagram, are electronic in nature. And so there's some overlap here between these rigid and these electronic controllers. And we've seen some recent work, of course, with flexible batteries and the like, that's really promising. But we took a different approach in the sense that we're looking at some fluidic control as opposed to electronics, and it uses entirely soft materials. So here in the top left, for example, is a CMOS-like circuit that's made only of elastomers or rubbers and the flow of air. We replace voltage and current in the electric domain instead with pressure differences in the flows of air in the fluidic domain. So it's basically an analog to electronic circuitry, and we can combine these logic elements to make things like sequential actuation on the top right, simplified control in the bottom left for coordinated motion and locomotion. And then we can even build in things like intelligence and perception and sensing directly into the soft structure of these robots. And this is, again, entirely in the fluidic domain. So we're not using any hard materials and we're not using any electronics. And so our recent work has focused on now translating some of these concepts for fluidic control to textile-based wearable devices. You've seen a lot of our prior work focused on things like elastomeric devices. What we show here, for example, some pneumatic McKibben actuators in a wearable. It would be really nice if we could get some textile-based versions of these, and especially if we look at the user in the video, the control system seems to be quite bulky, so control and power up here on the back, as well as some of the actuation. So if we could replace that with a fully textile-based system that runs only on air, we could serve the over 2 billion people that may need one of these assistive products like the wearable shown here. And we can overcome the limitation where there's a really lack of accessibility to this assistive technology because of things like cost or affordability, because of comfort and weight, portability. And so we think that a textile approach really will fit the bill here. And so to do this, we first set out, again, thinking about analogs to electronic components. We want to build textile-based fluidic digital logic and control. So we first needed something like a valve or relay. And so to do that, we thought we would use kinking of these textile sheets and channels to prevent the flow of air or other fluids. And so I have a schematic of the design that we chose. It turns out it's not as trivial as simply inflating a bladder to try to kink a flow pathway. It takes a lot of careful design to do this reproducibly and effectively. But we have a device here that works based on a set of two offset pouches that are one above and one below a flow channel. And when we inflate both of these offset pouches simultaneously, with the pouches each having a dimension L and an overlap fraction S, in this case showing a representative overlap fraction of 50%, what happens is as these inflate, these points B and C form kinks that prevent the flow of air. And so this yellow channel no longer allows the airflow. And so this is a really great approach that we found works pretty well, as I mentioned. But in terms of understanding it, we had to do some little bit detailed math in terms of solving this transcendental equation numerically. And so on the schematic here, on the figure, I show that the red solution to this model matches pretty well with our experimental results, those black data points. And those black data points are taken from the cross-sectional images on the right of the slide. And so this works pretty well, and we can see that as we increase the overlap fraction, we get higher and higher kink angles. But there's a really interesting caveat here, which is that as you go to overlap fractions that are greater than about 80%, you're no longer keeping this internal textile sheet in tension. Instead, it's in compression, and as a flexible but inextensible member, at that point, instead of forming these kinks and remaining taut, the entire middle element can buckle instead of forming kinks and still permit the flow of air. And so it actually takes a lot of consideration to design these kink valves effectively, but we did use this approach and found that for our work, overlap fraction of 50% yielding a kink angle of around 49 degrees worked very effectively. And so now we have the kink valve. That's one component of an inverter, or NOT gate for digital logic terms. And I have a picture of what that actually looks like here in the bottom left. It turns out that you also need the fluidic analog to an electronic resistor to make this textile inverter or NOT gate function properly. And so to build a fluidic resistor, we went with basically an open cell foam. And I talk a little bit about the need for the pull-down resistor here briefly. So if you think about supplying pressure to an actuator that helps the body move, you can inflate the actuator with the valve open. But when you close the valve, the actuator will remain inflated. There's no way for it to depressurize. You've just closed the channel. So by introducing this pull-down resistor, what happens is that in the inflated state with the valve open, we release a little bit of air. We sacrifice that, but we only drop the pressure by a few percent in the actuator. Whereas in the closed state for the kink valve, the pull-down resistor allows the actuator to exhaust completely and return to the ambient pressure. And so we tried some methods that use serpentine pathways between textile sheets. We found that those are pretty difficult to fabricate and align, and also that the resistance is hard to predict analytically. And instead, we opted for some open cell polyurethane foam. I show a micrograph here, as well as some characterization of the sheet resistance of this foam, again, thinking about this analogy to the electronic domain. And we found that it's very well characterized from some of our experimental results, and therefore easy to predict and design these types of systems. And so we have now the relay, which uses the kinking of these textile sheets. We also have the fluidic resistor built with this open cell foam. And by combining these, we have a textile inverter. And I show here experimental traces that are recorded during the function of this inverter. Essentially, what's happening here is that we have an input pressure normalized to 1 bar. And when the input pressure goes high, our output pressure goes low. So this is exactly an inverter or NOT gate, except in the fluidic domain. So we built a bunch of these analogs to digital logic systems and circuits. We made AND, OR, NAND, NOR. Some of these might sound familiar. We built what's called a functionally complete set of digital logic gates. What functionally complete means is that we can replicate any of the functionality of an electronic digital logic computer or system. It might take a little bit longer to do it, but we can get the functionality. And so then with these different types of logic gates, we decided to move towards integrated circuits. And here's our demonstration of one of these integrated circuits. We've built a controller that stores 1 bit of memory. And so this is composed of 4 inverters with some feedback. It looks like this. This is a photograph of the actual textile sheet-based device. The functionality is called a set reset latch because it does store this 1 bit of memory. And that means that if you press one of these input buttons that we show here, you'll push the output to high. And if you press the other one, you'll bring the output back down to low. And in the meantime, it will hold its state indefinitely. The push buttons were another design issue that we had to overcome, but we'd set up a system that looks like this. We have a pathway for airflow that comes from a supply of high pressure. And with the button in its resting state, the output is also high. Whereas if a user depresses the button with their finger with only a few newtons of force, the output goes low due to this pull-down resistor on the output line. And so we then took this SR latch, this integrated textile fluidic logic circuit, and interfaced it with basically a power electronics relay to a wearable hood, a hood actuator. This is a bellows actuator that's inside of a hood for thermal regulation. And you could imagine an application where a user might have limited overhead mobility. They can't reach up and easily put their hood on, but they want to still be able to thermal regulate, keep themselves warm or cool, depending on the environment. So maybe they touch a region on their chest or their sleeve to put their hood up or down with this entirely textile-based device that runs on air. And so we have here a picture or photograph of the device. With the device, we also wanted to test its ability to thermal regulate, which we did by using a small heater and thermocouple module attached to the top of the head. And we looked up the definition of a light breeze and found that it was about 3 meters per second. So we applied that with a fan that we measured the speed with an anemometer across the top of the head. And here comes a video that shows the actual fully integrated textile-based pneumatic logic system interfaced with this hood lift device with these bellows actuators. And so the researcher here is reaching over to press the set button in the set reset latch. We'll see that the hood comes up after just a few seconds of pressing the button, and it will remain in this donned or on state. And we can also watch the temperature at the top of the head increases over time. So we're achieving the desired result, and the hood will stay up. We go up to 20x speed here to kind of see that the hood stays on and the temperature of the head increases over time. And then after some time, maybe the user gets hot, they want to put their hood down, they reach up and touch the reset button to bring the hood back down. And so this is going to alter that internally stored single bit of memory to bring the hood back down again. And we'll see that that happens here in a moment after the researcher depresses the reset button. The hood will start to doff off the user's head, and the temperature at the top of the head will begin dropping. And so this continues for a few more seconds, again at 20x speed, to show you the rest of the process. And so we were really excited about this result. We thought to ourselves, this is great in terms of functionality. How about durability and reusability? And we probed that as well. And so I'm showing here a series of videos, first with 20,000 on-off cycles with one of these textile pneumatic inverters. Second here with 1 million flex cycles that we ran in the lab that simulates things like walking around or getting up and sitting down with one of these devices. We also did 20 machine wash cycles in a home use washing machine with commercial detergent. And we did actually 10 wheel passes with a pickup truck to simulate some really rough wear and tear on these devices. And for this textile-based inverter, we found that there was really no degradation in the performance. Again, thinking that when the input is high, the output is low, and vice versa. We see that in these experimentally characterized pressure traces. And And so we thought maybe we'll take this into the wild. We have a couple of PhD candidates in our lab here. The one on the left is testing out the device over some coffee and has the hood doffed to begin, and gets up and decides to put the hood on by pressing the set button on the integrated pneumatic textile logic circuit. And we'll see that that hood comes up as he's walking away. But one thing to note about this system that you don't see in the video, but is still present, is that on his waist is a CO2 canister, a small metal carbon dioxide canister of pressurized gas. And so we want to think about also soft power sources to try to replace this requirement for a hard and cumbersome and bulky source of pressurized air to operate this system. And what we identified also from this review paper, that it turns out that the power systems are quite underdeveloped in terms of utilizing soft materials as well. So we set out to build an entirely soft, in this case, textile-based energy harvesting system to meet the power needs of our logic and assistive device system. And so here's just coming straight out with a picture of it. We have essentially an insole device that harvests energy every time the user takes a step. And so every time you step, this energy harvesting device, EHD, is compressed through the system of check valves. It pushes pressurized air into this energy storage bladder, or ESB, which can then be used to power actuators, or it can just store pressurized air. The energy harvesting device inside the shoe is then again composed of these textiles that are heat sealed together. It contains this open cell type foam, in this case to restore the insole device when the foot is raised off the ground. And the entire thing is made of this really simple, inexpensive fabrication approach that, as I mentioned, is critical in terms of keeping these devices affordable and accessible to the people that need them the most. And so in this case, we're essentially just cutting layers of textile, heat pressing them together. For the energy harvesting device, we also have to inject this open cell foam and allow it to expand. Meanwhile, the energy storage bladder is constructed by the same method and consists of a bunch of cylindrical tubes that are made inside of this textile sheets. And so here's a video of what the typical operation of this device looks like. We have the user walking on a treadmill in our lab. In the top plot, we see a spike every time her foot hits the treadmill, characteristic of her just taking a step. And then in the bottom plot, now as we speed up the video, we see the pressure inside of the energy storage bladder around her waist start to increase. And we're going to approach up to 1 bar or 1 atmosphere of pressure here over a period of about a couple of minutes. So the device worked really well, worked as expected. We also said to ourselves, well, we don't want to demonstrate it, we want to also understand it, right? So we did some modeling and optimization of the entire system. In this case, where we treated the energy harvesting device inside of the shoe as basically a spring inside of a piston and cylinder, surrounded by these check valves. And the force that was applied to the outside of this piston is essentially the footfall or foot strike force as the user is walking. And we obtained that force by fitting a trapezoidal waveform to actual experimental data for the user, and then applied that to this system to model the performance. We found that that applies not only over short timescales as the user takes each step with this comparison between model and experiment, but also over longer timescales. So we show here that the performance over a period of a few minutes is captured pretty accurately by our model. And one of the trade-offs you can think about in terms of optimization for a specific application or user is that you can see that the smaller volume device for the energy harvesting insole reaches a higher pressure over time, but it takes longer to get there. And so if you need a higher actuating pressure for your assistive device, you might want to choose a smaller volume inside the shoe where you amplify the force of the foot strike to get a higher pressure over a longer time. But if you need to really generate a lot of power quickly without worrying about the maximum pressure, you might choose a larger volume that pushes more air during each foot strike. And so we looked at the power output, and thinking about those previous plots on the slide I had just shown, you can imagine knowing the volume of the energy storage bladder around the waist and looking at the change in pressure with respect to time to basically figure out the amount of PV work that we're storing over time in the system, or collecting or harvesting. And we compared that to the state-of-the-art for electronic energy harvesting devices. And we just saw several of these throughout the conference here, and a lot of really good work that's pushing the limits or boundaries of these electronic approaches up to even over, for example, a watt, which is quite impressive. This is really good for things like displays and sensors, things that monitor your health, functions incredibly well. But when you think about actuators that move entire appendages or pieces of the human body for assistance, power is key. You want to really push that power as high as possible. And we were happy to be able to report that we outperformed all of these electronic devices in the pneumatic domain with the work that I'm presenting here today. We also looked at the sensitivity to user attributes. So you can think about things like walking speed. We varied that by 300% and found that the effect on the maximum pressure and the rate of energy harvesting was not affected significantly. And in fact, collapsing those all down by normalizing to the maximum pressure showed that they all look almost identical. In addition, we looked at the factor of the user weight on the energy harvesting performance. And in this case, we compared 5 different people, both men and women, over a wide range of body weights, and found again that the performance is quite similar. In fact, normalizing it, they almost all look identical when we normalize by the maximum pressure that we store. When we don't look at the normalized results and instead just compare the maximum pressures that we can achieve, we also find that those match our expectation, essentially this black dashed line from our model, reasonably well. So we have a pretty good ability to predict the performance of this system. And then finally, we said we want to use this energy harvesting device for some practical applications. And I'm just going to show one of them here in the slides, which is to power a supernumerary or a third arm that's attached, in this case, to the user's hip. We see some photographs of the supernumerary third arm. This device is fabricated entirely from textiles that have been inflated with pressurized air, and we can achieve both an unactuated and actuated state to curl around and grasp objects. The operating principle that I'm showing here at the bottom of the slide is essentially that there's a support bladder that's always pressurized. That's this shaft that extends away from the hip or waist. And then we can curl or uncurl the grasping component of this third arm by pressurizing an actuation bladder. And I have a couple of photographs of this process in the top right here, where the user with their hands full is using the third arm to pick up a piece of waste paper and move it from one location to another. And that's also captured in the video shown here. Again, using only power or energy that's been harvested by our device, and achieving this hands-free operation to pick up this piece of waste paper and move it from one target location to another goal location. And so I'm going to summarize the work and wrap up now. I think that we'll be able to get pretty close to back on schedule here. Essentially, we just finished talking about the energy harvesting with this insole textile-based energy harvesting device, like, totally in the fluidic or pneumatic domain, and got performance that exceeded a lot of the outstanding work in the electronic domain, which we were quite excited about for powering these force-based assistive applications for the human body and wearables. And then looking back, we also talked about logic and control, again with this fluidic pneumatic systems that operate with these textile-based architectures. And we had to think about how do we achieve these analogs in these flexible but inextensible sheets? How do we get things like relays? How do we get resistors? How do we combine them into digital logic? And how do we make integrated logic circuits? And in doing all that, we achieved these integrated logic circuits that, with an appropriate pressure source, can then perform these assistive actuation motions. And so we're really looking forward in the future to trying to combine these avenues of research, having both the integrated energy harvesting and the low-level logic and control, all inside of the assistive wearable device. We're also looking forward to developing other textile-based technologies, including some ongoing work that we have on haptics as well. I'm going to stop here with some acknowledgements. We have a few references on the left side. I'm grateful for the recent support from National Science Foundation's Career Award. And I'm also really grateful for lab members Anoop, Barkley, Rachel, Faye, Jen, Coulter, and Marquise, as well as collaborator Vanessa. So with that, I'll wrap up here and take any questions.
Thank you, Professor Preston. It's a very impressive talk. I have a short question about the speed limit of your textile-based actuators and the whole system. So because it's textile-based, we know that you cannot really go down to really small scale. So how would you tackle the response speed of the system? Thank you.
Yeah, it's a great question. So we treat these more as textile sheets and don't even take advantage of the microstructure of the textile yet. And as you mentioned, that's going to limit our ability to scale down, improve the performance. Also, ultimately, I believe we would be limited by some considerations like, for example, speed of sound in these types of fluidic devices, and limiting the top speed for computation or operation and control. So those are definitely some issues that we will have to overcome and that we're actually actively working on now. A couple of options could include using much thinner textiles or even thin films to define these channels. So that's one of the things that we're looking at. And then also just optimizing the device design and performance outside of that as well.